one thing I wanted to say about this problem here is we're going to skip part C or part D because I didn't want to have you do part C because it's not stuff we're covering in standard level physics. This is a little bit more of an advanced problem, so we're just going to focus on problems A and B. Now, this is clearly a planetary motion problem, so I want to just write down all the formulas that are useful from the data booklet. So we have F is G big M little m over r squared. G is G big M over r squared. And G is also F over M. So with this idea in mind, it says show that the acceleration due to gravity near the moon's surface is 1.62. So here's what we're going to do. Gm is capital G big M over r squared. And we plug in our numbers. We're told that this is the mass of the moon, and this is the radius of the moon. And this is the mass of the moon, so I'll simply put in 6.67 times 10 to the negative 11th. M is 7.35 times 10 to the 22nd. And we're going to divide this by r squared, which is 1.74 times 10 to the 6th quantity squared. Now, you can try to be a hero and put all this in your calculator with all the weird powers and things, but I'll tell you, when they tell you to prove something like this, I would almost consider taking a little bit of a gamble. Like, try to get the answer once or twice, but then if it's taking you too much time, gamble on the fact that you've set it up right, and then just 1.62 meters per second squared. All right, now for part B. We're told that we have a mountain with a diameter like this, and here's the idea. The radius is 10,000 meters because it's 20 kilometers. Cut that in half to get the radius. So r is 10 kilometers. And here's the idea. We're going to throw this rock. It's going to have a horizontal speed, but let's not even worry about that. Let's first begin. Whenever you have these horizontal launching problems, here's what you do. Number one, get the time to fall. Then number two, then worry about horizontal. And you're going to want to use the formula D is V times T, or D over T equals V. So let's get the time to fall. To do that, we're dropping it from a height of 5,000 meters. So we got S equals 1/2 G on the moon, T squared, 5,000 equals 1/2 times 1.62 times T squared, and T ends up being about 78.6 seconds. Next, we can finally worry about this horizontal distance. So here's what we're saying. In 78.6 seconds, it needs to go 10,000 meters. So D is V times T, or V is D over T, which is going to be 10,000 divided by 78.6, and that's going to end up giving me about 130 meters per second. So that's question number 10, and we will continue with question number 11 in the next set of videos.